For our first seminar of winter term, that's a good reminder. When you do ask a question, Jennifer forgot to mention, press the button that says touch on the microphone at your table and just hold it down. The red light will go on while you're asking the question. Otherwise, Jennifer will remind you. So today we're very happy to have our first speaker of the winter term, as you can see, Kumar Venkat from Surya Technologies, is here to talk to us about supply chain, environmental performance, analysis, and optimization. And Kumar has quite an extensive educational and professional background, which I won't cover in 100%, but if I miss something, you can go ahead and cover it. But his BS in electrical engineering is from the University of Madras in India, and he has an MS in electrical engineering from the University of Texas at El Paso, and he did graduate work at various other universities, including Stanford and UC Berkeley, and has completed a graduate certificate here at Portland State in computer modeling and simulation. So with that, I will thank you in advance and look forward to your presentation.
Thank you. So, is my mic on?
It doesn't.
It does. Okay, so I can't tell. Okay, fine. That's fine. Okay. Okay. And is it okay if I just sit here and talk? Okay, great. So, thanks for inviting me here. I'm going to be talking about the environmental performance of supply chains, and let's see here. Yeah. So the motivation for this work is quite simply how to make business processes more resource efficient and therefore more sustainable. So we hear the word sustainability a lot these days in both business and government. And issues like global warming are now very widely understood to some basic degree, and they're no longer the exclusive domain of environmental activists. And it seems like we may be close to a tipping point just in terms of awareness and support for environmental protection and performance. So given that, it takes a while. Oh, sorry. So, for example, just a few examples to point out here. Large corporations like Walmart, surprisingly, Hewlett-Packard, Nike, ST Microelectronics in Europe, Intel, and quite a few others have made very strong environmental commitments in the last few years. And you might have heard of California's recent legislation to cap greenhouse gas emissions at the 1990 level. That's very aggressive. They haven't figured out how to implement that yet, but the legislation is in place. And if you read the newspapers in the last couple of weeks, and if you came across the Oregon Leadership Summit that actually happened, I believe, last week here in Portland, sustainability was front and center, and that was, it emerged as the key issue that needed to be addressed, as well as the key issue that will probably help Oregon move forward. So, given that, the intent of my work has been to try to respond to the need for quantitative tools to support a sustainable business. And if you actually look into this a little bit, you'll find that there aren't a lot of quantitative rigorous tools to help businesses and governments become more sustainable. So the intent here is to directly address and optimize environmental performance of complex systems and networks, and try to apply proven modeling and analysis techniques to create robust solutions. So why supply chains? Well, they are complex and interesting systems, but more importantly, they are at the foundation of global commerce. And so sustainability of business depends absolutely on the sustainability of supply chains. So they need to be addressed sooner or later, and probably sooner is better. Now, we hear a lot about green supply chains, and it often means looking into your suppliers' manufacturing practices if you're a big company. And, oops, sorry about that. That's my cell phone I need to turn this off. I thought I had it in the, sorry about that. So if you're a large corporation, you would be interested in your suppliers' manufacturing practices to make sure that they are doing everything in an environmentally friendly manner. But there's more to it. It's becoming fairly clear that we do live in a carbon-constrained world. So how we actually move goods is going to be very critical, and that's really a transportation, to a large degree, and that's the reason that I'm actually here to talk about this. Just to review a few trends very briefly regarding supply chains. First of all, they now span long distances. Right? We know that almost everything we buy come from thousands of miles away, including food, and they require significant use of fossil fuels to transport goods to consumers. And so freight transport is actually becoming a major source of carbon dioxide emissions as well as a result of that. And what we're also seeing is that, in general, throughout the economy, inventory levels are being quite low, and largely due to things like lean manufacturing and just-in-time deliveries. So what that requires then is a frequent replenishment of materials and goods throughout the supply chain. And depending on the product, not in all cases, but depending on the product, that type of activity can actually increase the energy use and carbon dioxide emissions and make the system less efficient than it could otherwise be. Now, looking at freight transport more directly, because of things like just-in-time deliveries, shippers increasingly value speed and reliability. They want what they really want is to ship smaller amounts more frequently in a more timely manner and in a more reliable manner. And what that means is that they actually favor the most energy-intensive modes, which are trucks and airplanes. Now, if you look at the impact of freight transport worldwide from an environmental perspective, freight transport consumes nearly a quarter of all the petroleum worldwide, and it produces over 10% of all the carbon emissions from fossil fuels. So that's quite significant. Just within the U.S., heavy trucks and light trucks together produce nearly as much emissions as passenger cars. So again, that's quite significant. Now, it turns out that heavy-duty trucks are actually very much part of the freight transport system, very critical to freight transport. And it turns out that fuel costs are actually often the second largest expense item for truck operators, typically after driver compensation. And so there's been a lot of effort to improve the efficiency of heavy-duty trucks. And most of these improvements have been mechanical so far, things like reducing aerodynamic drag, reducing idling, using hybrid drivetrains, and so on. What's probably been lagging behind, as far as I can tell, is system-level optimizations that might be able to yield additional efficiencies. Okay, I'll just skip that. It's just a little bit more statistics. So I'll start by talking a little bit about a very generic supply chain just to explain the type of analysis and optimization that I'm doing. We'll start with something very simple here. This supply chain just has 2 inventory stages, and as you can see, 3 transport links labeled supply 1, supply 2, and then delivery. So the final transport link actually delivers the product to the end user. And if this is a lean supply chain, what would happen is that the customer would demand a certain amount of the product, and then that demand information would propagate upstream through the supply chain. In a perfectly lean supply chain, that's exactly when the production would start, and then the materials and the goods would come downstream, and the product would get delivered to the customer as soon as possible. So in that case, there wouldn't be any inventory in those inventory stages, actually, or it would be a very, very small amount. And the 2 stages would be very highly synchronized. So keeping that in mind, if you go look at these results, what I've done here is that I've actually plotted here the carbon dioxide emissions from operating that simple supply chain. The carbon dioxide emissions are measured as kilograms of carbon dioxide per kilogram of product delivered in this case. It's a very simple generic case, and if you look at the lower curve here, the one that's almost pink colored there, the first point on the leftmost end, that actually reflects the demand that's placed by the consumer. Every few hours, the consumer demands something like I think something on the order of about 1,000 or a little more than 1,000 units, 1,000 kilograms of the product actually. So what happens is in that case, the product is actually manufactured almost just in time, delivered just in time, using, in this particular example, this particular simulation, using actually small trucks and delivering in small quantities just as the customer wants it. Now, if we were to relax this a little bit and say that perhaps we could actually deliver larger sizes each time that we transport something. So what I mean by the order size here is actually the shipment size. And if you also assume for the moment that we're using full truckload shipments, then what happens is as you go to larger capacity trucks, you become more efficient per unit of the product as far as emissions are concerned, right? But of course, once you've gone to the largest available truck size, then there is no further improvement if you were to increase the shipment size. Then all you would be doing is sending multiple trucks at the same time. Now, that lower curve is for a product that doesn't require cold storage or any kind of a climate control. And it might be it might be, for example, parts that go into a machine, for example, or parts that go into an automobile. So you don't have to worry about refrigeration or anything like that. Now, if you were doing a supply chain that involved food products, especially frozen foods and things like that, what would happen is that as your shipment size increases, your inventory levels would go up, and then you would be spending more energy then to maintain the product in inventory, such as refrigeration, right? So what would happen is as your order size increases, the energy, the carbon dioxide emissions would go down first and then go up again, and energy would actually follow a similar pattern. So you would actually see that there would be a natural point, a natural order size, where the emissions would be minimum and the energy use would be minimum as well. Now, if we take that same supply chain that we had, the same two-stage supply chain, and then if we go to another situation where the two stages are no longer really synchronized. What we did previously was we started with the lean supply chain and gradually made it non-lean, but the stages were still synchronized very highly. Now, if you have two really independent stages, and this is also fairly in a real-world scenario, and then you could actually look at the space this way. You have two axes where you can actually plot the shipment size or the order size for each of the inventory stages, and then you can actually look at the carbon dioxide emissions for the whole system. And what you see again, I don't know if it's really obvious here or not, is that there is actually a sort of a global minimum point where emissions are the lowest possible and the energy is the lowest possible as well. Right? And that's looking at the whole system together, not just one or the other transport link. So just to step back a little bit now, the way that we want to measure environmental performance is through an appropriate set of metrics. So for this particular problem, for the supply chain problem, what we typically use is energy or fuel consumption, carbon dioxide emissions, and financial cost. And a lot of times these are highly correlated because energy and fuel consumption would be fairly well correlated to financial cost in a lot of cases. And carbon dioxide emissions as well if you are using non-renewable energy sources. So the approach here is to directly analyze and improve the environmental performance by taking a system-level view of the problem, and then to try and offer a unique solution that complements other solutions. What we've seen so far in this work is that significant opportunities do exist for improving the environmental performance of supply chains. In some cases, you might get better performance at actually lower cost than before. In other cases, perhaps better performance without any cost increase. And the method that we are using to approach this is something like this. The modeling is a system dynamics type of modeling. With stocks and flows. I don't know if anyone here is actually familiar with that. No? Okay. There are some interesting courses offered at PSU in that area, by the way. And And then that's the modeling. The analysis is actually, the analysis algorithms are what I call static algorithms, where they're simulation-like algorithms, but you don't run long simulations. Instead, you actually try and get to sort of an average result very quickly by estimating the bounds for the performance. And we've actually developed some software to do this. And what the user actually sees is a very interactive, easy-to-use tool that hides all the computational details. What I'll do now is I'll actually go through 5 different examples to illustrate this some more. One of them is a manufacturing supply chain, and then a frozen food supply chain, a cereal supply chain, a dairy supply chain, and then a printer supply chain. So they're from different industries. There are quite a few food-related supply chains here because food supply chains are actually very interesting for analysis. So I need to state some assumptions here that we use to run these experiments. First, we're keeping the production batch sizes fixed in all of these supply chains. So what we're actually experimenting with are the logistics, the transportation, the storage, but not the production itself. I mean, in principle, you could vary everything, but that's one thing we kept fixed in this particular case. And we also assumed full truckload shipments. So what that means is that the shipment sizes are closely tied to the transport modes. Now, you don't have to have that in reality. You could have less than full truckload shipments if possible, if the logistics would allow for that in some cases. And then the shipment sizes could probably vary within some range, depending on what that transport mode is. But for these experiments, we're assuming full truckload shipments, just to make things a little bit simpler. And we're also assuming that we're using non-renewable energy sources, and that means energy use and carbon dioxide emissions are highly correlated. And so the experiments consist of essentially varying the transport mode and therefore the shipment size on each transport link in the supply chain. And when we do that, our software will automatically compute all the changes throughout the supply chain when we make one change to the configuration. And what we would be computing are energy use, emissions, and cost for each combination of our transport modes and shipment sizes. And for these experiments, we're going to be using 3 generic road transport modes: heavy-duty truck, mid-sized truck, and light truck. And we'll just label them H, M, and L in the graphs that we're going to show in a moment. And what you see here in this table is that the heavy-duty truck has a capacity of almost 3 times the mid-sized truck, but for a full truckload, it actually generates emissions that are only half as much as a mid-sized truck. So it's much more efficient. And similarly, the mid-sized truck is a lot more efficient than a light truck. So this sort of ordered in terms of the efficiency, the highest efficiency to the lowest efficiency here. And if you look at, if you're trying to optimize a system like this, if you have a supply chain that has uppercase L, transport links throughout in that network, and if each link can actually use one of M different transport modes, then the number of possible scenarios would be M to the power L. And for small supply chains, it's not a huge number of combinations. For example, if you had a supply chain with 5 transport links and 3 possible modes at each link, you've got about 243 possible solution points. And and if you're trying to optimize, you'll need to pick one of those. Now, if you had 10 transport links instead, that number goes to about 60,000 combinations. So that grows exponentially, and it grows pretty fast. Just for the purposes of this presentation, what I've really done is I've reduced the degrees of freedom quite a bit, just so that we can actually visualize the solution space and see things clearly. So in each example, I'm only going to vary the transport modes at 2 selected links and keeping everything else constant. So we'll start with the first example here. This is an automotive supply chain. It produces windshield wipers for cars. So we start with a steel manufacturing factory, and from there the steel is shipped to a stamping facility, and then to a wiper manufacturing factory, and then it goes to a car assembly factory. So what I've shown here also are batch sizes for the production at each facility, and the final demand from consumers every day. It's all per day in this particular case. And for every transport link, you also see the distance in kilometers as well as the transport mode. So in this particular diagram, what you see is that mid-sized trucks are used in all the transport links. And we are actually, in this particular case, even though it's not obvious from this diagram, we actually have a lean system here. And you'll see that on the next slide. I hope that's reasonably clear. Now that's just to show you what an analysis result would look like on something like this. On the first column, we have nodes and links. So we have various transport links as well as storage nodes and processing nodes. And the second column shows the modes, what transport modes we're using or what storage modes we're using. The third column shows, the energy or fuel used at each point or each link and each node. You'll notice that the storage nodes don't have any energy used because we actually decided, just for this simple example, not to model the energy used there because it's a manufacturing supply chain, and we just assume for simplicity that there is no energy used in the storage. It doesn't require refrigeration or anything like that. And the next column shows the distance traveled, and here you see the batch sizes in the transport as well as the average inventory levels, which are 0 because it's a lean system. There is no inventory kept at all. As things come in, they go out. And what's interesting for us is actually the energy use in gigajoules, and that's listed per link and node. Again, there's 0 for the storage nodes in this particular case, but that'll change in the next examples. So it's in this case about 62.48 gigajoules per day, and about 4,500 kilograms of CO2 per day. And the total cost, including the energy cost, including the transportation overhead, as well as the storage overheads, inventory costs, etc., in this particular case is about $2,200 a day. And that's just the cost of operating the supply chain, not the cost of producing anything. Now, you'll see that we're using mid-sized trucks on these 3 transport links here. Now, if we were to change all of those to heavy-duty trucks, then what happens is that our energy use, emissions, and cost all are reduced by approximately half. So that's quite substantial savings in that particular case because it's a simple manufacturing supply chain, and there is, we just assumed no energy use in storage. So in part, it also depends on our assumptions too. So to look at this in a little bit better, we can actually plot the energy profile as we vary the transport modes at different transport lengths. So in this particular case, we are varying it at the second and the third transport lengths. And what we are saying is, this is a light truck, this is a mid-sized truck, and that's a heavy-duty truck. And so we can vary that on both of those links independent of each other. And then we can look at what the energy profile looks like. And clearly, the lowest energy point is where both transport links are using heavy-duty trucks. And we'll see that carbon dioxide emissions actually are very similar in this particular case. They are very highly correlated, as we saw earlier. When you save one thing, you're saving the other also. And total cost for operating the supply chain is similar. So heavy-duty trucks actually give you the most optimum solution in this particular case. Okay. Now, if you look at another supply chain that's completely different, this is the food supply chain where ready-to-eat meals, frozen meals are manufactured and then distributed to stores. So the raw material is produced in farms. In this particular case, it's transported to a meat processing facility, and then it goes to a ready meals plant, and then to a retail distribution center, and finally to a retail store. And as before, I've indicated here, the batch sizes for the production at the various production nodes, as well as for every transport link, you can see the distance and the transport mode used. And for this case, the results look like that. And I know that's a little bit busy, but if you can just look at only the energy use here, and the emissions and the cost, then we'll make one change. We basically have two transport links that use light trucks and 2 that use mid-sized trucks, and we'll just bump all of them to the next higher capacity level. So the first to go to mid-size and the next to go to heavy duty here. And what we see here compared to the previous one is that the energy use goes down a bit, but emissions actually go up a bit. The cost goes down too. So what we did was we actually saved a lot of energy in transportation, but we actually ended up using more energy in storage because of the cold storage requirements. So in this particular case, because the energy sources are different in transportation and storage, it doesn't correlate very nicely as it did in the previous case, because in the previous case we actually didn't even model the storage energy. So in this particular case, the energy is saved and cost is saved, but we do have more emissions than before. And looking at this as before, just plotting the energy profile, again looking only at the first two transport links here, what you actually see is it's no longer the case that the optimum point is at the largest shipment size with the heavy-duty trucks. It's somewhere in the middle. So it has a sort of a concave shape. So there is still an optimum to be found here, but it's somewhere else in the middle. And that's with just two transport links. Obviously, with all the links added, it would be a more complicated picture. Right? And emissions are similar, but we already saw that the minimum for the emissions may not actually coincide with the minimum for the energy. So whoever makes the judgment here will have to do some trade-offs and find some point that actually provides the best energy use, emissions, as well as cost. So they all have minima, but they may be at slightly different points. Now, a third example is a cereal supply chain. Here, grain is harvested at this farm once a year. And this transport link is only used once a year for about a week or so, where all the grain is transported to a warehouse where it is stored for the rest of the year. And then from here it goes to a milling facility and then to a biscuit factory, cookie factory, I guess. And this example is from the UK. So, and then goes to a distribution center and a retail store. And as before, I've indicated here the distances and the transport modes and the end demand and so on. Now, here, I'm going to show only the energy profile and not in a lot of detail. What we are going to do here is just look at two transport links, actually, which is just this one, the one that goes to the milling facility, and then the one that goes to the biscuit factory. So what we see here is that the minimum here, just considering only these two links, is again at a point where both of those links are using heavy-duty trucks having the larger shipment sizes. And that's because this product doesn't require refrigeration. It might require some modest climate control, but not refrigeration as in a frozen food supply chain. And we also see that the energy profile is quite sensitive to the transport modes on this link, but not so much on this link, and that's simply because this is a longer link. This is a 100-kilometer link, and this is a 1,000-kilometer link. So that's the reason for that. Oops. And then my fourth example is a dairy supply chain, where milk is produced at really at three different places, and then they're all shipped, and they actually converge here at the dairy facility here. And then from here, a truck carries the repackaged product to four large customers. It goes to a retail store as well as three large customers, such as restaurants and so on. But it's one truck that basically makes a route and delivers all four and then returns back. And what we are showing here is basically that these links are using light trucks, and this link is using a mid-sized truck as it stands. And if we plot the energy profile for this, here what I've done is I've actually combined, there are three links, the three transport links coming into the dairy, and what I've done is I've actually changed them all together, so just in order to reduce the degree of freedom, so we can actually see something in 3 dimensions here. So here I'm actually, on this axis, I'm changing all 3 links together, to the same transport modes. And this is the here I'm changing the transport links. The transport mode used in the routed delivery to the customers. So what we see here is that the transport links to the dairy they really want to use light trucks. Whereas here on this link, mid-sized trucks seem more optimum, and one of the reasons, actually the reason for that is milk is produced daily in small quantities, and it actually doesn't make sense to transport that in larger quantities than the production size and then store it somewhere for 2 or 3 days because it's a perishable product. So it actually, and there's a refrigeration cost, so it actually makes sense to transport exactly what's produced each day using whatever truck size is appropriate, and then to distribute that the same day. And here the truck size is a little bigger because it essentially combines the product from 3 different places, so it aggregates, so it's actually carrying a larger amount of the product. Okay. And excuse me, the last example here is a printer supply chain. This case study is actually from Hewlett Packard, I believe from their Vancouver facility, where they used to make either inkjet or deskjet printers. I don't remember exactly. And this is actually from the early 90s, where they would assemble the printers here in the U.S., and the parts would come from actually the integrated circuits would come from Asia. They would be manufactured in Asia and then shipped to the U.S. The printer mechanism would be made in Japan and then shipped to the U.S. And some of the printed circuit board materials and other things would actually come from U.S. suppliers and transported by truck. And once the printers are manufactured, they would be sent to the U.S. distribution center as well as to Europe and Far East distribution centers. And all of these very long distance links are by ship, and everything else is by truck. And in this particular case, they had a lot of inventory problems at their Europe distribution center, where sometimes they would have too much inventory and sometimes they would just run out of product and not be able to satisfy customer demand immediately. So what they would do is occasionally add air freight to expedite some number of printers just to supplement the existing distribution in order to just meet demand. And so just taking a look at that sort of a scenario, if you look at the energy profile of this system, and if we vary only 2 things here, one being all the transport links going into manufacturing, into the U.S. manufacturing, the three transport links that we saw. There is a integrated circuit manufacturing, there's other materials, and then this printer mechanism. And if we vary those together in order to reduce the degree of freedom again, and on this axis, what we're showing is the percentage of goods transported to the Europe distribution center that are sent by air. And initially, that's 0. So when that is 0 and you're using mid-sized trucks on these transport links, the energy is about 123 gigajoules per day. Now, in this case, if you decide to add air freight, and if you say that about 5% of the goods sent to Europe would be by air, then what that does is it actually increases the energy used from 123 to 157 gigajoules. Now, you can then look at the system and see if there's something else that you can optimize or modify to reduce energy use. And you can actually, if you go from mid-sized trucks to heavy-duty trucks on these transport links, then you can come back to 132. In other words, you can go from 123 to 157, but then you can come back to 132 by making a change elsewhere. So what this shows is that you may be able to actually improve service levels and responsiveness of a supply chain without necessarily degrading the environmental performance too much by making changes elsewhere in the system. So that's another way of looking at the environmental performance of supply chains, where you're not trying to save money or even to improve the performance overall, but you're just trying to improve the responsiveness of the supply chain and then not degrade the environmental performance from where it was before. So just some comments on what we've seen in these examples. When storage doesn't require high energy use, larger shipment sizes and more energy efficient transport modes are actually preferable, as we've seen in the manufacturing supply chain and also to some extent in the grain supply chain. Of course, there is a constraint in terms of the inventory holding cost. Obviously, you don't want to increase the overall cost of the system. Now, when the storage is energy intensive, as in say, a frozen food supply chain, the optimal shipment sizes and transport modes are going to vary depending on the product, but a lot of times intermediate sizes would actually work pretty well. And if you had a fixed production schedule, as in milk production, for example, combined with refrigeration requirements, then the shipment sizes would need to be aligned with the production batch sizes in order to minimize energy use and emissions. Now, stepping back a little bit, so where do we use all of this? There are a few different application areas. The first is simply achieving overall cost savings from reduced energy use in supply chains. As the cost of energy goes up, this could be critical. And then the second thing that's actually getting a lot of attention now is meeting either voluntary or mandatory greenhouse gas emission targets. A lot of companies are signing up for targets like that. Even when they're not mandated, they're actually voluntarily doing that. Or they're at least getting to the point where they're reporting their own energy use and emissions from year to year and trying to show a decreasing trend. Also, another emerging area is actually emission calculations for use in offsetting carbon footprints. A lot of companies and even some individuals now are trying to be carbon neutral. So once you've done everything possible to reduce emissions, the final emissions that are left over could actually be offsetted by purchasing the appropriate credits. And that money would go to actually developing clean energy sources elsewhere. So what we're finding with our work with supply chains is that supply chains are very highly suited for rigorous analysis and optimization of environmental performance. And the approach outlined here could help with the transition to sustainable business. There's more information at my company website if anyone is interested. And this whole presentation is actually online. Rob has a link. Maybe he can forward that to everyone, in case you want to look at it again. And there are other documents also at my website if anyone is interested. And also there's contact information if I can be of any help to anyone. And I just wanted to mention also finally that sustainable business is going to require a lot of quantitative tools. What I've outlined today is just one of many different solutions that are needed. And just to mention a couple of them briefly, now one requirement is going to be some kind of a simplified life cycle analysis for both businesses and consumers. So what we've done with supply chains is to some extent life cycle analysis, but not cradle to grave. It's just a subset of that. But what I think a lot of businesses want is something that's simple to use, that looks at the entire life cycle of products and entire life cycle of business activities. Also, mapping and analyzing material and energy flows either within a company or within a group of companies or in a region or economy-wide is going to be critical. And it goes under the names of industrial metabolism, regional metabolism, etc. And transportation actually plays a very central role in all of this. So I think it's very appropriate that we're talking about it here at the Center for Transportation Studies. So that's all I had. Any questions? Yes.
It seems as though there's a trend in the U.S. towards privatization of freeways and instituting tolling. Is that applicable to your research? Would that added cost have a significant enough impact to affect the way these chains operate, or is that relatively minor?
I have actually never looked at that. So I don't know how it compares with the other cars at all, actually. So really, I've just focused on the energy cost, if anything. Yeah. So, yeah. Yes.
Here. Okay, well, I'm sorry. I've never been in this room before. It's sort of outside the scope of what you're doing, but when you use the word sustainability, it kind of implies this question. Suppose you start off with 10,000 units of some kind of emission, be it carbon dioxide or whatever, and you manage to, through efficiencies, get it down to 5,000, right? So, 50% reduction, right? So that's great. And carbon dioxide isn't necessarily the best example of this because it is processable by, natural resources.
Okay.
But at the same time, to a certain extent, it's instead of the planet, overheating in 50 years, we're only overheating in 100 years. And so we're still not at a sort of a sustainable point. I was just wondering if you had given any thought to that sort of next step to where we go from, a 50 to 100 to a 200-year time horizon to a sort of an infinite one.
Yeah. Well, I mean, that's it's a very big question, obviously. But, I mean, my personal thoughts are that what we're doing here is obviously, it just barely starts to scratch the surface. But what we're also doing is buying some time, right? So if we can go from a 50 to 100-year time frame, then we have got that much time to develop new technologies, new processes, etc. And that's really all that we're doing at this point. So. Yes, sir.
Have you incorporated any rail in the supply chain, and how would that affect environmental issues as far as cost?
Actually, it's a lot less carbon intensive. I haven't used rail in any of these examples, but I have used them in other examples elsewhere, and they're part of the tools that we're developing. And I don't have the numbers handy here, but I think that they're actually even more efficient than heavy-duty trucks. So they would be very efficient. The problem is that they're perhaps not as fast and timely as some of these other modes, and therefore they tend to be used less these days, where everything needs to happen fast and on a short time frame and just in time, etc. So that's the issue. But I think it's probably a very good alternative if you could plan ahead for it. Yes.
For your trip analysis, you normally didn't show the return trip. I mean, in the dairy example, you showed the delivery truck returning, but not going back to the farms.
Correct.
Is that normally considered or not considered?
Oh, well, it would depend. So what we have in our tool is a way for you to actually provide that information on each transport link. So you can actually say, well, if the return trip is actually used productively, then you don't have to consider that in your analysis, because somebody else is using it and they can count the emissions from that for their product, for instance. But if the return trip was empty, then we would actually consider that in our product analysis, in our supply chain. And so that in that case, the emissions would sort of double approximately for that link. Not quite double, because the truck might be returning empty, so it's not carrying load. So the energy use is going to be a little bit lower and the emissions are going to be lower. But yes, it should be part of the analysis. Yeah.
How about using biofuels?
Biofuels? Yeah. Well, I mean from our point of view, you could actually input any fuel type in our software. So, we could analyze anything. With biofuels, I mean, there are obviously some interesting issues, and you do have to look at the life cycle of the fuel a little bit more. Actually, where the fuel comes from, how much, in fact, fossil fuel energy it takes to manufacture the fuel, right? And I think some interesting studies have been done on that, including, I think, at UC Berkeley, they've recently done some work on that. And I think it turns out that there are still advantages, but perhaps not, in some cases, not as much as people think. So, yes.
As you pointed out, there are several million possibilities to get a good from point A to point B.
Yeah.
And so you're calculating the cost for each possibility, and then you look for the minimum, right?
Well, I mean, obviously your optimization algorithm needs to be smart if you want to actually do an optimization of that whole space. I mean, you can't really calculate millions of things. You could calculate perhaps a few thousand solutions probably. And, as you're exploring that space, I mean, the first few solutions might tell you in which direction to go, for instance. So you can actually eliminate several other possibilities. So, the trick is to eliminate things as much as possible so you can actually get to find the optimum point as quickly as possible. But in real life, we are not hoping necessarily to actually provide somebody an optimal solution, because people are using all kinds of supply chain analysis and management tools already, and some of them are very expensive and complicated. And we are actually, here what we're trying to do is, in a typical real-world situation, we are taking somebody's existing supply chain and telling them what the energy use and emissions are going to be in that supply chain. And if they have 2 or 3 other alternative configurations, we can analyze those configurations and tell them, what the impacts are going to be for those. We would also like to optimize, and there are some very nice algorithms available, and we're working on some, but But as I said, there are already other tools that do optimization of supply chains without considering environmental performance. So we're trying to be a sort of an add-on to that at this point. So, yes.
So is this software and the programs that you've been developing, are they available just to anybody, or
yes,
what
anybody,
are you guys
anybody
focusing on right now?
who is willing to pay.
Yeah.
But I would say, for instance, and I'm not supposed to talk about the software too much here. So I wanted to make this more of an academic presentation, actually, which is why I didn't actually mention the name of the software either. But it's, at some point, if people are interested enough here at PSU, I'm happy to provide some free copies that we can install on the computers here. If somebody wants to use it for research, use it for teaching, etc., we can certainly do that for free. So we won't charge PSU anything. So. Yes.
Actually have, sir, one clarification to
Yeah.
make sure I understood something correctly, and
Right.
then there's a question from someone who's watching on the web.
Okay.
And there were several cases where the heavy trucks were lower energy and lower carbon emissions
Right.
than light trucks.
Right.
And that's going to be the case if you have enough goods to fill up the heavy truck, right?
Yes.
So if you only have a very small amount to fill up a light truck, then the light truck's obviously going to be.
Right,
But in
right.
your examples, it was always a large amount of.
Well, okay. So
Or
I think I had enough demand at the end of the supply chain to be able to fill up a heavy-duty truck if we needed to. And sure, if the demand is at a very low level, obviously you wouldn't do that. Or there is another alternative too. Another way of looking at it is, in that case, we could ship once a month, for example, and then still fill up a truck. So then we have to look at the cost of the energy cost of shipping versus the energy cost of storing goods for a month, and then supplying out of the storage. And that's the whole idea here. So.
And then one of the questions on the web is sort of wondering about how you might be able to expand or generalize this type of analysis to look at changes in the transportation system. So, for example, if you were to build a superhighway, or I would add a rail link or add some other change to the system, could you adapt this?
Oh, yeah, absolutely, because we could take any of the transport links in the supply chain and then put in whatever transport modes that we want to analyze. If you're using trucks today, we can try rail, for example. And if the distances change, that's very easy. We just change the distance on the transport link, for instance. And if that means we are adding a few more stages to the supply chain in order to transition the goods from one mode to another mode, for example, let's say we're replacing a single truck link with a rail link that goes most of the way and then maybe truck after that, we can easily make those changes to our model in the software for the supply chain. So we can do a lot of these what-if experiments quite easily, and that's the whole point of this, actually. So you can explore that. Even if you don't use a heavy-duty optimization algorithm, you can actually sit down and explore the space with all these alternatives. Yeah.
It seems like it'd be a pretty short jump to actually be able to use these tools to do locational analysis for different firms. How often do you put the firm location and variable, make the distance variable to look for efficient?
Yeah, well, let's see. If I understand your question correctly, the tool as it stands now, it takes distance as one of the inputs on all the transport links. And by location, what you mean is the name of a place or some coordinates of a place, or
Yes.
coordinates of a place.
Yes.
So that would be sort of an extension of what we have done. It wouldn't affect any of the core processing that we're doing, but it would certainly change how we take in inputs. So we would have to take the geographical coordinates and convert them to, and then figure out the distance between the points. So that would be an add-on thing, and we haven't done that so far, but that might be something to look at, actually. Yeah.
'Cause I think it'd be really beneficial for a firm to, with this type of, sustainability in mind,
Right.
to, use this type of analysis to figure out where they want to be.
Yeah, well, yeah, exactly. So, in fact, one of the things that we are suggesting people do with this is actually evaluate alternate supply chain configurations, including, if you're a company that's sourcing goods from different suppliers in different places, you could actually look at different combinations of suppliers in different parts of the world and see which combination is the lowest impact scenario. And certainly, I think some sort of a geographical information there would make it easier to use. So right now they have to put distances everywhere. So somebody has to calculate distances or go to distances.com and get the distances, I suppose. Yeah, absolutely. And that's something that we probably need to look at in detail at some point soon. Yes. Thank you. Yes.
Have other countries imposed a CO2 tax on their freight sectors?
Not that I know of. I mean, Europe obviously has signed on to Kyoto, so they've actually agreed to limit emissions, and they're not quite there yet in terms of the implementation. So I don't think anyone has actually imposed a tax yet. They're trying to use a cap and trade scheme where they would limit the CO2 to some upper limit. And then you could then buy and sell credits. If you save CO2, you would be able to sell those credits to somebody and actually, then your company would be more profitable, not only because you're saving energy, but you're also saving CO2 and selling those credits. Yeah. Yes?
I realize this question is kind of out there, but I know they've developed hydrogen-powered SUVs. Have they done any research into hydrogen-powered freight trucks or anything like that?
Actually, they... not hydrogen powered that I know of, but they are working on hybrid trucks, just like hybrid cars. And in fact, I believe it's UPS that's using some of these hybrid trucks in an experimental way for local deliveries. And I forget in which part of the country. They're not using it for long distance because I'm not sure it offers advantages for long distance. But for local deliveries, they're trying that hybrid trucks. Yeah.
Kind of out there too. Kind of the correlation between cost and CO2 emissions.
Yeah.
I mean, for instance, here in the United States, the main emphasis for business is lower the cost, maximize the profits,
Right.
regardless of the emissions.
Right.
I'm wondering, you mentioned Europe. I'm wondering, is Europe kind of going the other way and realizing that the emissions may be more important than cost with the trading with the Kyoto? Is there
actually, in Europe, my understanding is that governments are being a lot more proactive about it, and they're basically, regulating these things. So, they have agreed to limit CO2 emissions, which means everybody has to comply with that at some point, sooner or later. In fact, they've got other regulations too for that cover things like product disposal, like computers, for example. What do you do at the end of the life cycle, for instance? So they've got a lot of these regulations in place in Europe that we don't have here. And that actually is driving, to some extent, actually, industries' performance and what their actually technologies are developing. And to some extent, it affects the U.S. as well because companies have to sell in Europe. So they are trying to comply with that. So to that extent, it's important here. But it's driven largely by government regulation in Europe, though, not from the private sector.
So I guess we're still not quite at the tipping point, as you were saying earlier.
Tipping point in terms of awareness, yes. Not in terms of action. But I saw a very interesting statistic just a couple of weeks ago. They had done an opinion survey just around the New Year time, and I think they found that something like 3/4 of the people in this country are actually aware of global warming, and it's among the top 3 or 4 issues. For a lot of people in the new year. And so that I thought was very interesting because a half a dozen years ago, most people hadn't heard of it. So that, seems like we're getting closer to a tipping point, but, just awareness so far, yeah. Yes?
I guess when you mention that corporations are showing more environmental awareness, I must admit my thoughts are that they'd probably focus on their own operations rather than necessarily their supply chain and push that environmental impact off on the suppliers who are providing that transportation. So do you see a better awareness of bringing this into that overall corporate picture?
There is some. For example, we are talking with Hewlett Packard, and they actually have a whole team of people working on stuff like this. So they are interested in the logistics and the whole supply chain, actually. And so they are interested in using tools like this. So Nike, for example, is interested in this. And some of them have either internally developed a proprietary software or no software at all, but just spreadsheets and things like that. But they are trying to consider the whole supply chain. And they're doing it, of course, not because of regulation, but voluntarily. But what that means is the smaller companies are not going to be so eager to do it. The larger companies have the resources to do it, so that might be a difference.
So before we thank our speaker, I'll remind you that next Friday we have Charlie Hales from HDR, former Portland City Commissioner. He'll be talking about how Portland is taking America back to the future, the national streetcar movement, and the changing urban landscape. So with that, thank you very much, Kumar. Thanks for